rotate it around like twice.
Yeah. So you'll need to do more than one. What's my pattern? What pattern am I working with this structure? It's going to fall into one of four categories, right? Allylic anion, allylic cation, allylic radical, or diatomic. Which pattern is this?
Allylic anion.
It's an allylic anion. So once you know that, what else do you know? You know how to push the electrons because it doesn't change. It doesn't matter how big the molecule is. If the allylic anion pattern is present, the flow of electrons is always here. Turn that lone pair into a pi bond, turn that pi bond into a lone pair. Now that's going to get me to here. That carbon is negative now. And I have a double bond here, one here, one here. Is that pattern going to repeat?
Yes.
Mm-hmm. Are the arrows going to be any different for this structure than they were for the first one? Right? Do I need to go to not Calhoun's? That's not open anymore. Do I need to go to Piggly Wiggly and get some different types of arrows to draw the resonance form with that structure? It's going to be the same exact flow of electrons. The lone pair is going to become a pi bond. The pi bond is going to become a lone pair. So I'm going to put this here, that there, and then this here, and then this doesn't change. Now, can I get here? You see the pattern again? So somebody tell me what you would do there.
You would draw the lone pair would become the line inside of the hexagon.
So
and then
wrong pen.
Yeah, like that. And then the other one would become a lone pair.
Like that. Yes. And that'll get me to that structure. Is that right? So I gave you kind of a rule of thumb for resonance forms because, again, one of the other parts of this is identifying the donor and the acceptor. It's very important. I spent, I think, 10 minutes of the lecture this morning in part 2 explaining resonance to students who had already taken part 1, either over the summer or last semester. Don't get caught in that loss of not understanding these fundamental concepts because they're important all the way through the class and all the way into the second part. All right, so I gave you a rule of thumb that if you counted up the donors and the acceptors, you can have a rough estimate of how many resonance forms are possible. So over here, excuse me, we had one donor. If we count here, if we start here, that's my donor. And then we had 1, 2, 3 acceptors. So we should at minimum get 4 structures. And you can see we have 4. We could actually get a 5th one. If we took this one and did resonance on it, we could get back to a structure that's similar to the original. Is that right? Because the pattern is right here. Can somebody do that one? Tell me or at least tell me what you would do.
Your the one connected to the double bond would go above the CH2 to become a lone pair.
Like that?
And then yes, and then your actual lone pair would then go to that line inside the hexagon.
Mm-hmm. So you end up with this, wouldn't you? Where all your, and if you look at what happens based on the original structure, what do we do? What changed? We've seen this before, just with a different molecule. But what changed relative to the original structure? Over here. That's what we're comparing. Did anything change?
Double and single bonds change places.
Yeah, your double bonds inside the aromatic have been rearranged. Now they're in a different location. All right, that's good. Thank you for that. And thank you, Chase, for walking us through those couple of examples too. Appreciate it. What about here? Look at the structure on the right. Tell me how you're going to get there from the structure on the left, and tell me what changed. And tell me why oxygen is negative.
Is it because did the lone pair over the N hydrogen to the 2
Mhm.
form to become the double?
So I keep using the highlighter. So to here, is that what you're saying?
Yeah, and then the double bond on attached to the oxygen became another lone pair.
I agree with that. So when you have a system like this, even though it's not an allylic anion or a cation, it's similar. And because of that, you can push the electrons the same way. Of the systems that we know, which one is this most similar to? Of the 4 systems we talked about, which one is it most similar to?
Allylic anion.
Good. It's similar to that. So the electron flow is going to be the same as that. All right. Go ahead. How do we get the formal charge on oxygen?
Oxygen has 6 valence electrons, and there are 7 bonded to it, so you get the -1.
Good. Good. So a formal charge, again, if you notice, I'm trying to keep all the skills that we've already talked about and incorporate them into all the examples. So you keep seeing it over and over again, repetition, muscle memory. So when you get to a point where you see formal charge, a formal charge or a charge on an atom, you already know, oh, that atom's charged because it has more electrons than it's supposed to, right? Let's go to these examples here. This is different. This is the reverse of what we're doing up top. You're given the arrow and you're asked to draw the structure that you would get based on the arrow that's present. All right, what would I get for the first? What is that arrow indicating in that example? Anybody? Notice where the arrow starts. It's starting at one of the pi bonds. It ends on an atom, right? So it's not becoming a bond. What is it going to become?
Is it a lone pair?
A lone pair. I want to stress that every bond, you learned this in general chemistry when we talked about covalent bonds, and I don't know if I've stressed it enough, but every bond is made up of 2 electrons. It's 2 electrons being shared between 2 atoms if it's covalent. So when I break a bond and put the arrow on an atom, that means that arrow is indicative of that bond becoming a pair of electrons. So now I have and this was positive. Now it's neutral. Am I missing something?
Isn't there a positive charge on the nitrogen at the end?
Indeed. And we can calculate it too, right? Nitrogen normally has 5 around it. Now it's got 1 from each double bond and the lone pair, so that's 4. So the charge should be +1. Excellent. What about here in the next one? Any questions about that? Don't let me rush you. If you got a question, don't hesitate to ask it. Let me fix that. That looks sloppy. All right, what about here?
Oxygen is gonna have a double bond, and then the CH2 is gonna have a lone pair. Oh,
No, you're right. You're right. That's on me. Go ahead.
is the arrow being drawn to the CH to be a lone pair, or is that just another double bond?
Look, where does it stop? Does it stop on the atom or does it stop on the line?
It stops on the line.
Okay, so that's your answer. If the arrow stops on a line, it's becoming a bond, a double bond, or pi bond. If it stops on the atom, it's becoming a lone pair. So right here, we're going to write this like this. Does that make sense? Are you following that?
It makes sense.
Mhm. So it stopped on the line. And notice what I did, right? What's the overall charge here? Overall, right? I have a negative charge on oxygen, a -1 charge. I got a -1, +1 charge on the CH2. So what is the overall charge?
Would it be
Zero.
neutral because they cancel out?
Yes, they do cancel. Exactly. Over here, what's the overall charge? You can say it. You're not wrong. Is it 0 also?
Yes.
Yeah, it's 0. So both structures are neutral. That's one of your rules for resonance, is that your resonance forms need to have the same charge. So if this is neutral, this also has to be neutral. So they should have the same charge. All right. Anybody not following that? Why we push those electrons there and made a pi bond as opposed to making them a lone pair? Right. There's no atom there to accept those electrons as a lone pair. But if you put it between these two atoms, then it becomes a pi bond. Why do you think that, and this is related but unrelated, why do you think that the resonance, well, the structure on the left, why do you think it did resonance to get back to the structure on the right? What's the goal of any process in the universe? I said this a long time ago, a few weeks ago.
Is it balanced?
Okay, balance. I like that answer. That's true. Which can also be interpreted as stability. So the structure on the right with all the electrons and the charges is unstable. And so it's going to do resonance to get you to the structure on the right, which is more stable, because although they're both neutral, having those actual full charges is not a good thing, right? You want to eliminate that. So you do resonance and take those electrons and delocalize them so that nothing is charged. And that's why you go from the structure on the left to the structure on the right. You go from a less stable to a more stable structure. All right, what about here? What do you think? What's the new resonance form going to look like for that? Look where the arrow stops. What does that tell? And what pattern is that? Anybody? What pattern is that? right? Isn't that an allylic cation? Is that right? What's the structure going to look like on the right? We know it's going to be a ring. Where's the pi bond going to be? Where's the plus charge going to be in the structure on the right?
The pi bond would be across from the other pi bond.
Right here.
Yes.
And then where's
And
my
then the plus charge would be at the top.
good? And it's this carbon right here that becomes positive. Why did it become positive? What did I do to it to upset it? For lack of a better term.
You took away one of the bonds, so ultimately took away an electron.
Took electrons away from it. And because of that, it became positive. So anytime you remove electrons from an atom, it becomes electron poor. So it has a positive charge. If you give it electrons, it becomes electron rich. So you're either going to neutralize it or make it negative. We're going to talk more about that later. All right. Can somebody, if you're able to annotate, if you can see the annotate tool on your toolbar for Zoom, can somebody draw the structure right here? And don't worry about if you get it wrong. This is the time to get it wrong, so it can be corrected. A wrong answer is only a stepping stone to the right answer. So can somebody put that in, annotate it, if you're able? Let me see. Let me check.
I could try.
Let me check the security and make sure you can annotate. Yeah, you can annotate. Go right ahead.
So like, would I like share my screen or something?
Y'all, do you have a little pencil tool on your Zoom toolbar?
You gotta click the view options thing at the top, and then it says annotate under.
Oh yeah, I see.
Yeah, okay, good. Thank you. Is it Mag? Is that right?
Yeah,
Is that okay?
yeah.
Okay, I just want to make sure. I don't want to call you that, like, that's not my name. All right, I see. Thank you, Sade. Okay, good. And I want to recommend, if you don't, if you have never seen it, there's a notebook. They sell them on Amazon, and they have the pages are kind of like this. Let me see if I can show you on here. The pages look like that. They look, oh, sorry, my bad, Kadir. Let me get you back to where you're supposed to be. I just screw that up. I did. God dang it, Russell. All right, my bad. I'll show it later. I didn't know that was gonna happen. All right, you can finish it. You're on the right track too, that's great. Okay. Okay, excellent. Does anybody disagree with that? That's exactly right. That's exactly right. Put your Cash App, if you use Cash App, put it in the chat. So I've been buying a lot of lunch lately. I paid my debts though, didn't I, Reagan?
Yes, sir, you did. Thank you.
All right. Good. That's good. right? So you have, the reason we're working through these examples is because, again, you got to get used to both. You got to get used to putting the arrows in and following the arrows if they're already there. So that's the whole purpose of this exercise. Let's finish these down here. Thank you, Kadir. Let's see, I gotta clear it.
No problem.
Yeah, let's see. Okay, oh, you already cleared. All right, bet. All right, let's go to the next set of examples, and then we're gonna shift gears. This will be the last that we do for this section on resonance, but you're gonna see it again. You will definitely see it again. It says draw a second resonance structure for each ion, right? What is it asking us to do? And what's the first thing you need to identify before you can do resonance?
You have to identify the donors and the receptors.
Excellent, excellent, excellent. Right, and they have to be adjacent to one another, right? So we can see that pattern. We can see a pattern right here where we have a negatively charged oxygen and then a pi bond or carbonyl next to it. So this is going to be the donor because it's negative, right? It's trying to get rid of those electrons. And the pi system becomes the acceptor by default. If you identify one or the other, then if you identify the donor by default, what is bound to is going to be your acceptor if it's an acceptor, and vice versa. All right, what system does this mimic? Allylic anion, allylic cation, allylic radical, or diatomic. Those are the four classes of systems where you'll be able to do resonance. So what does this fall under? What category?
Is it allylic anion?
Okay, great. If that's the case, what's the flow of electrons? Because it doesn't change from that very basic example that we did when we first started talking about this. It never changes. So what's the flow of electrons for an allylic anion? And let me say this, the electrons are always going to flow from the donor to the acceptor, but there's a specific pattern here, right?
So would the lone pair become a double bond?
Yes,
And then the double bond that's originally there gets transferred to a lone pair?
like this. Are you saying put it here and then here?
Yes.
Yeah. That's exactly right. So now so what does the other resonance form look like? Right now, oxygen is negative. We have a double bond here, and then a hydrogen here. Yes or no?
Yes, that's correct.
All right. Let's go to the next one. What system does that fall under? It's two atoms together. It's not allylic. So what system would that fall under?
Diatomic.
It's a diatomic. And now here's a question that we have to always think about, right? So we know we need to identify the donor and the acceptor. In this case, what are my options for donors? Anybody? We know lone pairs are donors. What are my other options? Well, there's one other option.
But double bond.
Double bond, pi bond. So pi bonds and lone pairs can be donors. And then for my acceptors, what are my options?
The nitrogen.
Okay, so it's a cation, some type of cation, or a pi bond, right? So in this case, if my nitrogen is the acceptor and the pi bond is the donor, what's the flow of electrons? Because it's always from donor to accept. That's the reason I keep stressing that, is because when we get to the next section, dealing with acids and bases, and the next section after that, dealing with nucleophiles and electrophiles, that concept doesn't change. It's always from donor to acceptor, or from source to sink, or from electron rich to electron poor. That's how electrons flow, because electrons are negative. So they're always going to move towards what's positive. So my pi bond is the donor. So what would I do in this case? What do I need to do?
The double bond would form a lone pair on the nitrogen, and then the carbon would become positive.
Come on, man. Come on. That's exactly right. Here. And then this is still CH2 also, but now it's positive. And notice the charges, overall charge for both structures is the same, and they just interconvert. Who was that? They just gave that answer.
Michael.
Michael. Good. Put your name in the chat also. Your cash out in the chat. All right, let's go to the next one here. Any questions about that diatomic? All right, what about here? Do you see the pattern or a pattern? What?
Is this another allylic anion?
Exactly right. How would you move the electrons? If it's an allylic anion, the flow of electrons does not change.
The double bond attached to your oxygen would be turned into a lone pair,
Mhm.
and then the original lone pair would turn into a double bond.
Yes. That you again, Chase?
Yes.
Oh, I guess I gotta buy you lunch too. You've been on it today. You must have ate a good breakfast. Here. Oh. Is that right? Is that what you meant to say? But is that what you said?
Yes.
Okay, good. All right. Good. Any questions about that? All right. One more. I'm gonna leave that open for somebody to annotate it. And you can see the pattern also, can't you? Right? And this is going to be my donor. This is my acceptor. So this is going to follow just like all the other allylic anions that we looked at. Like that. All right. I'm going to send out two. There's a guy at the University of Maryland. He has some really good videos on Lewis structures and drawing Lewis forms. So I'm gonna send that video when I send the videos for class today. Yeah, he's really good, because I think part of the disconnect sometimes, especially because if you notice, we've been using skeletal forms the whole time ever since we learned what a skeletal form was. But I think sometimes there is a disconnect sometimes when you look at a skeletal form and don't understand like what it is. But this guy is excellent with Lewis forms, and I'm gonna send that to you so you can refresh, because it should have been taught in part 1, but sometimes some instructors teach it, some instructors don't. Part 1 of CHEM, by the way, my bad. All right, let me introduce you to the next topic. And let me also go back. And there's let's see. What I was saying earlier, there's actually a notebook that you can buy on Amazon. And I don't know if you can make that out, and I can't zoom on it, but it actually has a grid on it, like a hexagonal grid. So you can get used to drawing the proper bond angles for organic structures, especially for skeletal forms and for rings. I'll find the link and I'm gonna put that in there. You don't have to buy it. I'm not asking you to spend any more money than you already have to spend, but it is a great resource. I have a couple of them that one of my friends put me on, and I didn't realize they even made them. But it does help if you have trouble drawing structures, if you have trouble drawing the chains and the skeletal forms, it'll help a lot. So I'm going to put a link to that in the announcement today. All right, let me. Page here. All right. So this next section is we're going to be introduced to what we call intermolecular forces. And you've heard of a lot of these already, more than likely. You'll hear me refer to these as IMF, right? So intermolecular forces are exactly what that term sounds like. Inter, which means between. And then molecular, right? Molecules. So these are forces. I'm just going to give this a very basic definition. Between molecules, right? There are a lot of your IMF, a lot of the intermolecular forces that we observe are dictated by functional groups. So certain functional groups do certain things and they allow for certain intermolecular forces to be present, right? So this is the intermolecular forces are dictated by functional group. Sometimes they can be dictated by the solvent. And sometimes by structure. Right. So when you have a molecule and it's around other molecules like itself, I want to make that plain up front. When we're talking about intermolecular forces, if I have, let's say if I have an alcohol, I have a beaker full of cyclohexanol. For the purpose of this discussion, we're talking about how this cyclohexanol interacts with another molecule of cyclohexanol, right? So if I have a beaker full of this stuff, what are those molecules doing? Like, how are they interacting with one another? So inter, right? How does one molecule out of Avogadro's number of molecules per mole interact with the other molecules around it in a solution that's all the same thing, right? So when we start talking about the different forces, this is how you have to think. You have to be thinking in terms of how that molecule interacts with other molecules around it, or how it interacts with the solvent in which it's dissolved in, like something like that. All right, we're going to talk more about that. but I'm going to give you an introduction to the different types. So we have 4 types. We have 4 types of intermolecular forces. Right, we have what we normally refer to in general chemistry as an ionic bond. I'm putting bond in quotes, but it's really, I think I talked about this a couple of days ago, really an electrostatic attraction. Right, you got something that's positive like sodium, and then something that's negative. And those, because of the opposite charges, they hang out, right? Each one of them is trying to satisfy the need for, or the desire, I'm saying desire in quotes because atoms don't really have desires, but the desire for neutrality. And so the sodium, the positively charged sodium hangs out with the negatively charged chlorine, right? And it's such a tight attraction that at room temperature, sodium chloride is a solid, right? It's table salt. That's how tight that attraction is, right? But this one is different from the other types. The other types of intermolecular forces are what I like to call covalent forces. And you've heard of Van der Waals forces, or you also probably have heard it referred to as London forces, right? London forces or Van der Waals forces, every molecule experiences this, everything experiences Van der Waals forces. Right, so every molecule is going to experience Van der Waals forces. So a lot of times, if you see when we're talking about this, and you see a question on the exam, what intermolecular forces are present here, Van der Waals is always present, no matter what. Right, then there are other forces, and I'm listing these in terms of strength. So dipole interactions. That's the second type of covalent force. And then hydrogen bonding. And I'm just giving you the terms. We're going to talk about each type of force separately with examples, but I'm just giving you the names, the terms. All right. So this is, if we think about this in terms of how strong each force is, the strength is increasing as you go from London forces to dipole to hydrogen bonding. This is the strongest of all of your intermolecular forces, all the covalent forces. Right, all your covalent, out of all the covalent forces, hydrogen bonding is the strongest. Can somebody tell me where in nature where you can find like hydrogen bonding? Oh, and let me rephrase that. In the body, in the human body.
DNA.
DNA. Who was that? Kadir, was that you?
Michael.
Michael, yeah, that's exactly right. DNA is the 2 strands of the helix are held together by hydrogen bonding, right? It's a very, very strong attraction, and it's a very strong covalent force. So much so that DNA doesn't just randomly unzip. It takes a lot of energy to get DNA to unzip or to pull those strands of that double helix apart. All right. All right, we got 3 minutes and I don't want to go further with this because I want to send you some information first, send you a video to watch, and then when we come back, we're going to have a discussion about intermolecular forces as they relate to boiling point, melting point, all other physical properties, and as they relate to water solubility. Right. So we'll talk about that later. Any questions? All right. If not, we're going to stop.